Now that we've introduced the topic of determinants, we're going to explore this topic a little bit deeper, looking at some properties of this property of a matrix. So first thing, if we have a square matrix, which we need to calculate determinants, we're going to look at what row operations will do to that property. And the most important one is this first one, that if a multiple of one row of A is added to another row of A to produce a matrix B, then the determinant of A is equal to the determinant of B. Also said, that is, that if I take the row operation, a constant times one row plus another, that leaves the determinant unchanged. If I interchange two rows, then I'm going to be multiplying the determinant of the new matrix by -1. Or said also, if I have row I swapped with row J, that multiplies the determinant by a factor of -1. We can understand maybe where this one comes from, that when we have the definition of determinant, I have a bunch of those -1 factors. If I swap the rows, that's going to mess up those factors by a factor of -1. Everything's going to be kind of moved around one spot. And the third one, if I take one row and I multiply it by k to produce another, then the determinant of B can be said to be k times the determinant of A, or said also, if I have a constant, the scalar multiplication of a row, that multiplies the determinant by that factor. So alpha row I into row I gives the determinant a new factor of alpha. This last property can be said in a different way by thinking about factoring out a common thing in a row. So if I'm trying to calculate the determinant of a 3 by 3 matrix here, remember that the vertical bars are representing determinant, and I have a row with a common factor of k, what I can do is I can pull out that factor k, factor it out, and multiply it by the determinant. That's the same idea as we were saying in part C of this theorem, is that I can do scalar multiplication. That's the same as just multiplying the determinant. I can think of it equivalently as factoring out something in common, and that's how we're going to use it in this section. So the point of this theorem is to calculate determinants of large matrices. That can be difficult sometimes because it's a lot of calculations that I need to do. In fact, without this theorem, the amount of calculations that I have to do for an n by n matrix is n factorial, which is a lot of calculations, especially as n gets big, but this is going to reduce it a lot, and we'll see that with some examples. So first example, compute the determinant of this 4 by 4 matrix. And note that in the previous section, we talked that you can use a cofactor expansion across any row or any column. So we're going to pick the row or column that has the most zeros. And in this case, that's going to be row 2. Zeros are very nice in the determinant process because the whole term will just go away as we're multiplying by those entries. So if I'm going across row 2, the only non-zero entry I have here is the 5. That is in the second row and second column. So that's how I'm going to determine the factor on the -1, the exponent. -1 to the second row, second column, 2 plus 2, that's a +1. And then I look at the determinant of the minor matrix that I get if I erase the second row and second column. So I'm left with 1, 3, 4, 2, 6, 10, 2, 7, 11. But now, what I'm going to do is instead of looking at this determinant and looking at the determinant of 3 2 by 2 matrices, I'm instead going to row reduce, and that is going to either leave the determinant unchanged or multiply by a -1 or by some factor. So in this case, if I want to row reduce, I'm going to try to zero out these entries right here, the 2's, using the pivot in the top left corner. And I can do that using the two operations, -2 row 1 plus row 2 into row 2, and -2 row 1 plus row 3 into row 3. So doing those operations are going to leave the determinant unchanged. That's from the theorem on the previous page. And I will get the new matrix out 100, 301, 423. And I'm going to be multiplying by that entry of 5. I can't forget that entry, that's still there, 5 times that determinant. Now in this case, you could maybe stop right here and think that you could do the cofactor expansion along column 1 or row 2. Both those have only one non-zero entry, but we can just continue to row reduce until I get it into triangular form, which we saw in the previous section makes it much easier to calculate determinants. So I can do this by swapping row 2 and row 3 to get it into triangular form. Triangular form meaning that I have all the things below the diagonal or above the diagonal are zeros. And since I had to do a row swapping interchange, that gives me a -1 factor that I have to multiply by that determinant. That's the cost of doing that row operation. Now that I have this determinant and I have this upper triangular matrix, I can just multiply the entries on the main diagonal. 1 times 1. Make sure we have the -5 here times 1 times 1 times 2 will give me a -10 as my determinant. So you can try this problem out yourself using just the cofactor expansion, and you'll see that it will take you much longer to do, and you'll have to perform many more calculations to do it. Sometimes the cofactor expansion is the quickest way to do it, but this row operation thing is another tool that we can use to simplify finding the determinant. Let's look at another example, and in this one we're going to look at that third row operation where I have this scaling of one row, and we're going to think about it as factoring out a number. So if I am taking this matrix and I want to find the determinant, I don't have a nice row or column that I can do a cofactor, so I'm just going to row reduce into triangular form. So first thing I want to do is get a 1 in the top left corner, and since I have 3 things that I can take a 2 out, noting that we could always take a value out and we're just left with some fractions, but it's nice to deal with whole numbers, I can take a 2 out of this first row and just take it out of the determinant and recognize it as 2 times the first row divided by 2 times the rest of the determinant, or with the rest of the matrix. Then, using this new matrix, since I have a 1 in the top left corner, I can do my row reductions. The main ones, when I take a multiple of one row plus another, leave the determinant unchanged. In this case, I'm going to do -5 row 1 plus row 2 into row 2, and -7 row 1 plus row 3 into row 3 to zero out the 5 and the 7 here in that matrix. When I go through those calculations, I am left with the matrix 1, 2, 3, 0, -4, -8, 0, -8, -11, noting that I still have to multiply this determinant by 2 since I factored that 2 out before. Then I want to get a 1 in that second row, second entry, so I can factor out a -4 from both those entries, and I'm going to get a 1 and a 2 from that -4, -8. And I can just bring that -4 outside of the determinant. Finally, I can take 8 times row 2 plus row 3 into row 3 to zero out this entry below the pivot, and I will get a upper triangular matrix with the main diagonal 1, 1, and 5. I multiply those values together, and I multiply by the 2 and the -4 that I factored out earlier, giving me an answer of -40. Once again, if you want to practice the cofactor expansion, take this example and go through those calculations, and you'll see that you'll have to perform many more calculations to do that instead of just this row reduction process. So now we're going to get to an example how we're going to be dealing with these problems in real life, and that is if I have this 4x4 matrix, I'm not just going to use just cofactor, I'm not going to use just row reduction, I'm going to use a combination of the two and find when it fits me best. So this problem, I could just go through row reduction and go through only that and get to the answer, but that will actually take me a while, especially since I have a nice column or a nice row that I can do a cofactor expansion. In this case, that is going to be down column 3 because I only have one non-zero entry. So doing the cofactor expansion, the only thing I'm going to have is the one non-zero entry. That non-zero entry is the third row and third column. That's where I get this 3 plus 3 on the negative 1. Note this is the A sub 3 entry. This whole thing is the 3 cofactor. So the power on negative 1 is 3 plus 3. That's some notation from the previous section. And then I am left with a negative 2 times the determinant of this matrix. And now I'm going to do some row reducing to get it down to upper triangular form. So I can factor out I'm going to row swap row 1 and row 3 to get a positive 1 in the top left corner. So I'm row swapping row 1 and row 3. But when I do that, I have to multiply my determinant by a negative 1. That's where I get this negative 2 becomes positive 2 on the outside. Then since I have a 1 in the top left corner, this is now a pivot in the top left corner, I can zero out the entries below it by doing the row operations negative 4, 1 plus row 2 into row 2, and negative 2 row 1 plus row 3 into row 3, leaving me this matrix, this determinant, times 2, and nothing else has changed in that determinant because those row operations do not affect the determinant. Finally, I want to get rid of, I have my two pivots here, 1 and negative 1. I want to zero out the entry below it. So to do that, I could do negative row 2 plus row 3 into row 3, and that'll give me 2 times the determinant of this upper triangular matrix. 1, negative 1, and 6 are the main diagonal entries, so I multiply all those together, and I'm left with a positive 2 on the outside of that, which gives me a negative 12. Note that maybe at this point you wanted to do negative, or factor out a negative from that second row. So you could write this as negative 1 times 2 times the determinant of 1, 2, 4, 0, 1, 13, 0, negative 1, negative 7. And you can go through it that way. There's not one way to row reduce to get it into echelon form. And note that this is row echelon form, that upper triangular matrix that we have. So a square matrix we're going to see is invertible if and only if the determinant of A is non-zero. And this is really our first kind of foray into why is the determinant important, is that it is related to the fact of whether a square matrix is invertible or not. So let's look at the definition of the inverse of a square matrix, a 2 by 2 matrix, if it's invertible. A inverse is going to be 1 over AD minus BC times the matrix D, negative B, negative C, A. And note that A is invertible if and only if AD minus BC is not 0. And then we know that the determinant of ABCD, this matrix, is AD minus BC. And that's where we're saying that if this determinant AD minus BC equals 0, that we don't have an inverse. The matrix is not invertible. So that is our first useful theorem, is that we can determine if a matrix is invertible or not by looking at the determinant of the matrix. we saw a couple sections ago that we have this large theorem of all these ideas that correspond and are equivalent to saying that a matrix is invertible. And now we have one more, that being the determinant of the matrix. Also, when we're thinking of the transpose of a matrix, if we have a square matrix, then the determinant of the transpose is equal to the determinant of the matrix itself. We can kind of see that because since we can do a cofactor expansion across any row or any column, the transpose switches all the rows and columns, and we can think about just doing the cofactor expansion across a row instead of a column, and we would get the same exact result. A nice property of the determinant is that I have this multiplicative property. The determinant of AB is equal to the determinant of A times the determinant of B. And these multiplication properties are very nice because we do not have this property for just matrix multiplication necessarily. So let's use that property to determine the matrix, to determine the determinant of A cubed, if we know the determinant of A is 5. So the determinant of A cubed, we could rewrite as the determinant of A times A times A. Using that multiplicative property, we can write that as the determinant of A times the determinant of A times the determinant of A, or the determinant of A cubed. And that will give us 5 times 5 times 5, or 5 cubed, will give us a 125. Also, for n by n matrices, we can show that a matrix is singular, that A is singular here, if the determinant of B is non-zero and the determinant of AB equals 0. First, I want to remind you that A is singular means it does not have an inverse. It is not invertible. In that case, that means that the determinant of A is equal to 0 from the previous page. So if I'm going to look at the determinant of AB here, I can write that as the determinant of A times the determinant of B, and we have that this is going to be equal to 0. And since the determinant of B is non-zero, then we must have that the determinant of A is equal to 0. This is the zero product property that we use so much in algebra, that if you have two numbers multiply to give you 0, and one of them is non-zero, the other one has to be 0. And the determinants that we're calculating here are just numbers. So therefore, since the determinant is 0, we have that A is singular, which means that it is not invertible. It does not have an inverse, and we saw that that means a lot of other things related to matrices and linear independence that we've seen before. So last example here, given that A is invertible and the determinant is 3/2, what is the determinant of A inverse? And we're going to use the fact that A times A inverse is equal to the identity matrix to find this. And also note that the determinant of the identity matrix, we'll look at the 3x3 identity matrix. Since that's an upper triangular matrix, we can just look at the product of the main diagonals, which will always just give us 1. So we always know that the determinant of the identity matrix is just 1. And in this case, I'm going to rewrite I as A times A inverse. Using the multiplicative property, this is the determinant of A times the determinant of A inverse. And I know what the determinant of A is, that's 3/2. So I can write the determinant of A inverse is 1 divided by 3/2, or 2/3. It is the reciprocal of the determinant of A. This introduces some properties of the determinant. There are many more uses for it as a very nice property that we can continue to explore later on in this course.